Hi, I'm Jackie, and I'm going to be talking to you about open versus closed loop systems in control theory. An open loop system is something where there's no feedback. You have an input, you put that input into your system, and you basically walk away and say whatever happens, happens. So an example of that is if you want to wash your clothes, you put your clothes in the washing machine, you set a timer, and then hopefully your clothes come out clean. But if your clothes are dirty, there's nothing in the system that tells the washing machine to try again or run it for longer. So that's an open loop system. You have an input, you put it through the system, and you get an output. Closed loop system is where we use feedback. So if these clothes are dirty, in a closed loop system, what happens is the output, cleanliness of the clothes, gets fed back in to affect the input. So if your clothes are dirty, it's actually going to change the amount of time that you run your laundry machine so that it becomes clean. So that's an idea of closed loop feedback. So you see here that we have a summation. Basically that's saying we have this input, we have the output, and what's going into the system is no longer U of S. What's going into the system is your error. If your clothes are dirtier than you want them to be, there's some sort of error, and that error is going to trigger your system to keep going. And so these are just arithmetic equations that describe how to simplify this block diagram. And it's really easy to just memorize these equations. So if you have a G of S, once you solve this closed loop system, what you're basically doing is turning it into an open loop system. So you're solving this and you're simplifying it into an open loop system with the transfer function G of S over 1 plus G of S. Here's another example if you have gain or if you have another function affecting your output before it goes back into your input to create error. I'm going to start talking to you about stability. In some systems, when you have an input, you can put that into your control system and it can blow up. You can put in a sine wave and all of a sudden that sine wave gets a ton bigger and it goes unstable. So we don't want that to happen. That's why we use a ton of different methods, which you'll learn in control systems, as to whether it evaluates the stability. You start out with a function like this. You have your G of S written out or given to you. First you want to simplify to find your closed loop transfer function. That's what we did over here. So we do the simplification. Now what we see here is we can view the zeros and the poles. Zeros and poles are just terms used to describe the transfer function. If you set the numerator equal to 0, what value of k does k have to be? So 0 for this function is k equals 0. And if you set the denominator equal to 0 and solve for your various variables like s or k, those are your values for your poles.
So I will be talking to you a little bit about unit step, PID control, and introduction to root locus as well. As Jackie mentioned, we have an input that we're trying to give a certain output, and we have all these variables that are trying to disrupt our system. So we're trying to tune certain gains we like to call proportional gains, derivative gains, and integral gains in order to get the system to perform the same way under many different circumstances. So this is an input. We'll have a given input and we have a given output. That's our blue curve here. Depending on how we tune each of these proportional, derivative, and integral gains, we're going to get different outputs. The way we like to analyze these systems in order to see whether or not our proportional, our PID controllers, our gains are doing the right things is we like to look at root locus plots. In a system like this, we have a output which tends to oscillate a little bit around our desired output, and I'm going to draw a little dotted line here to show the level of damping, which will help us in plotting our root locus. So in this system, it still oscillates a lot, so we can plot this point somewhere on the left plane. We plug in different PID values, and we see what the output looks like. And in that way, we can start filling up this graph here. So something like this will be somewhere in the left plane since it comes to a stable point. This is our unstable region. And everything in this region is unstable. Usually a sign of that is if the real value is positive, because it's in the right half plane. So something like this, we'll have a value around here. We'll change our PID and get a different output. Let's use a different color. Let's try purple. Something that looks more like this, where it takes longer to mellow out. We'll have a lower damping ratio, and it'll be closer to our y-axis. You can do this over and over again and we'll get some points here, and we can start to construct what looks like a fluid line that gives us more information about our system. Your location of your poles and your zeros will kind of dictate what this graph looks like. But the closer you get to this y-axis, the less damping you have, and the closer you get to neutral stability, which is represented by this y-axis. So this is neutral stability. What that basically means is it's in a constant state of oscillation. It's stable, so to speak, but it's also oscillating constantly and it never gets to an output.
Can you draw me the graph of neutral stability and draw a little graph of what unstable looks like? Because I'm not sure what you're talking about.
I'm glad you asked that. Here's our input. So if I understand correctly, you'd like me to look at more of the neutral stability. Okay. So, for neutral stability, we have something of this sort. And it just goes on and on and on, you get the picture. So, what's happening here? There's no damping. So these asymptotic lines are going perfectly horizontal to one another. It's going to land somewhere on our y-axis. It's stable in the sense that it's not changing its form, but it's always oscillating and it's never getting to our desired output, which is right in the center of the amplitude.
So what would unstable look like?
Unstable. So in an unstable system, if you can imagine for a stable system, we have something that goes to zero. Not to zero, but to our desired output, so that's it. We have decreasing there. In the opposite case, let's use a different color. For unstable, what do you think would happen? You would have this curve, and whoop, it gets bigger and bigger and bigger. So we're always increasing at an exponential rate, and that's going to land us in our unstable region.
Awesome. Thanks so much.
No worries.
Hey guys, today we're going to talk about how to transform differential equations to Laplace transforms. So we have a differential equation which is defined as this one, and we're going to try to solve it for the initial conditions of zero. And one trick that you need to know is that look at Laplace tables. Because when you look at the Laplace tables, second derivative is defined as s squared y of s and then minus s by this one. And then when you look at the first derivative, you're going to see this formula. And when you look at the y of s, you're just going to find this. And since the initial conditions are zero, when you do the calculation, you will find that the differential equation of this one can be transformed as the Laplace equation of that one.
When you went from the big long equation to this ys over u of s, why are you doing that? Why do you want y of s over u?
This is the output of our system, and this is the input of our system. So if we want to make a block diagram, we need this transfer function. So if you have a system of linear equations, of differential equations, we can just transform this differential equation to a block diagram easily by using transfer functions.
Oh, that's super interesting.
This is the tricks of ESE 505 to time response of first order systems. Let's say we have a time function defined as this one. What is the time constant and the steady state gain? It's actually really easy to do. We just divide by a naught, and when we do the calculations, the steady state gain is b naught over a naught, and the time constant is. Don't get distracted by the zombies outside, and we need to finish this lecture in 5 minutes. The unit impulse is just the inverse of the Laplace transform. You can look at the tables. And for example, for the first order system, if you have k over tau s plus 1, the inverse of the Laplace is this. The step response is pretty easy for first order systems. It's just the gain, k, initial slope. Let me go this way, which means we're going to take the derivative of the differential equation and evaluate it at t equals to 0. For the first order system, it's just k over tau. We're going to look at time response of second order systems. Second order system is defined with the transfer function of this one. And if you want to find the damping coefficient and the natural frequency, we just rewrite the whole equation in this format. And as you can see from this one, the natural frequency square is square root of a naught, and the zeta is taken from making the algebra. The settling time is pretty simple, 4 divided by zeta times natural frequency. And if you want to find the zeta from the step response graph, all we need to do to look at the peaks and find the delta by taking the ln, natural logarithm, and the zeta is just followed by this formula. You can check the log decrement on Google to find more information. Any questions?
Thank you, Bruce.